So here we want to figure out how high a geosynchronously orbiting satellite should be. What that means is that this satellite will always be above the same place on the Earth. For example, it's always going to hover above Ecuador. So for that to happen, it has to be orbiting at exactly the same rate of rotation as the Earth. And here's something we have to understand in order to approach this problem. We have to understand that a planetary body that is orbiting, such as the Earth around the Sun here, there's one attractive force between those two bodies, which is the force of gravity. And that force of gravity is, therefore, the centripetal force that is responsible for keeping the Earth in the uniform circular motion in its orbit around the Sun. And again, I guess that wouldn't be a uniform circular motion because it's an elliptical orbit, but you get the idea. So the trick here is that we can say that the force of gravity felt by the Earth from the Sun is equal to the centripetal force, or the radial force, needed to keep the Earth in orbit. So if we wanted, we could substitute what we know, definitions for these values. We have an equation: the force of gravity equals the gravitational constant times mass of the Earth times mass of the Sun over the distance between them squared. And this is the distance between the centers of the Earth and the Sun, not the closest edge to the closest edge. That's not the way it works. It's the center. And we could set that equal to the centripetal force, which we have just seen is mv squared over r. And that r is the same value, the distance between the center of the Sun and the center of the Earth. But here we're talking about a satellite orbiting the Earth. So let's not even worry about the Sun anymore. But the point is, we can use this same equation, because the same thing is true. The centripetal force to keep this satellite orbiting the Earth is exactly the same as the gravitational force through which it's attracted to the Earth. So here our expression for the gravitational force is the gravitational constant times the mass of the Earth times the mass of the satellite over the distance between them squared, and again, to the center of the Earth from the satellite is that distance, and the radial force is the mass of the satellite times its velocity squared over that distance. So the main trick behind this problem is to be able to set up this equation. And you can do this with, this is a common thing you can do with problems involving orbiting. Just say that the force of gravity equals the centripetal force. And we want to solve for r here. But that isn't our answer, because our question is how high above the Earth should the satellite be? But what we're solving for here, if we solve for r, is how high above the center of the Earth. So we have to realize that we're going to have to adjust that value when we get toward the end of this problem. So we could go ahead and start solving for r, and we can simplify this a lot. We can cancel out the mass of the satellite, because it appears on the top on both sides. And we can also cancel out 1r, because it appears on the bottom on both sides, once over here, and twice over here. R squared is like r times r. So we can cancel out one of those and get rid of the squared. And that simplifies our equation a lot. So let's see. Do we know all the other variables besides r? We know g is the gravitational constant. We can look in the back of the book or Google that. The me is the mass of the Earth. We can Google that. I think it was on a previous slide in this chapter. And v squared is the mass, or this is the velocity of the satellite squared. So this satellite, we don't know how high it's going to be. The higher it is, the faster its speed is going to be. So we we don't know what v squared is exactly until we figure out r, so we got like a chicken and the egg problem here. But what we can do is define the velocity, that speed of orbit, in terms of r. We just saw that we can define the speed of something going in circular motion with this equation. We know that the speed is proportional to r, the distance from the center of the circle, and inversely proportional to the period. So what we're going to have to do is, even though it makes the equation more complicated, we're going to have to take this definition of r and that definition for v, and insert it for v here. And we get this equation here. And you may be saying, well, we don't know what t is. We don't know what the period is. But yes, we do. We can totally figure that out. We know that the satellite is orbiting with exactly the same rotational speed as the Earth is. For every one rotation the satellite does, the Earth does one rotation. We know exactly how long it takes the Earth to do one rotation, 24 hours. So the tricky part actually becomes putting 24 hours into seconds, because seconds is the SI unit for time. So that's a lot of seconds. Alright, I'm going to start a new page. I'm going to take this equation here and start solving it for r. All I've done here is move r up from the bottom on the left to the top on the right, and I squared the term on the right that was supposed to be squared. So 2 became 4, pi became pi squared, t became t squared. And now I'm moving t squared from the bottom on the right to the top on the left. And I'm moving 4 pi squared from the top on the right to the bottom on the left. And that leaves r cubed alone. So now we just need to take the cubed root of both sides. And we have solved for the variable we want to solve for. Now we just plug in some numbers. So when putting in the numbers, it's important to find the mass of the Earth in kilograms, which I've done here. And we already put time in the SI unit of seconds. And this gravitational constant is just a matter of Googling it or looking in the back of the book. And our calculator gives us an answer. But remember, this is not the answer we're looking for. What this r value is the distance between the center of the Earth and the satellite. We want to find the distance between the surface of the Earth and the satellite. So what we need to do is subtract the radius of the Earth from that big distance that we just found. And you can just Google the radius of the Earth or something. And that leaves us with our actual answer of 3.6 times 10 to the 7th meters, or 36,000 kilometers roundabout. And that is about 6 times the radius of the Earth.